In order to understand the fossil record as Darwin and Alfred Russel Wallace and all these old geologists understood it, you have to understand that it's kind of like your kitchen trash can. What do I mean by that? Well, if you take a look at your kitchen trash can, you have trash, and you put trash there every day. Every single day you put trash in, there's another layer of trash on top. This layer was put there on Tuesday. This layer was put there on Wednesday. This layer was put there on Thursday. This layer was put there on Friday, Saturday, Sunday, and then the top layer is today. So, if I were to find one particular piece of trash and I wanted to know how long ago it was that I made that trash, say there's a banana peel down here in the very, very bottom, chances are I ate that banana on Tuesday, because trash cans reliably segment themselves into these nice layers, which you might call strata, going up here. What do I mean when I say that the fossil record is like this kitchen trash can? Well, fossils only develop in sedimentary rock, and sedimentary rock develops in floodplains and swamps and other kinds of low-lying areas. So let's say I have an organism that dies down here in this floodplain. This organism is going to be some kind of dinosaur. Now, it dies down here in this floodplain, and as it rains, water is going to wash down in this floodplain, and as the water washes down, it's going to erode away this hillside. It's going to carry clay and silt and little particles of rock and all kinds of sediment along with it, and this body, this dinosaur body, is going to start getting buried underneath that sediment. Notice how we're filling in the bottom of this area where the dinosaur died, just like we filled in the bottom layers of the trash can. So now it's been a little bit of time, right? The dinosaur died, millions of years ago. At this point, the sediment has really built up, and it's compressed together, and it's formed what we call sedimentary rock. Sedimentary rock is like shale and limestone and that kind of thing. So here we have this nice little layer of sedimentary rock, and we have a new organism, let's say, and this organism is a bunny rabbit. The bunny rabbit comes a little bit later on, but it dies in the same floodplain, and it also gets buried in sediment. But that sediment is going to have to build up on top of the sediment that we already had. So we have different layers of sedimentary rock, right? And the deeper we go down, the older the rock is. Down here at the bottom, we have the oldest rock, whereas up here, we have today. Today we have people walking around up here on the surface. Now, will this human leave his own fossils behind? Potentially, if they die in a floodplain or in a swampy area, which develops into sedimentary rock over the course of millions of years, yeah, he could leave his fossils behind. And there's a lot of humans, so I'm sure somebody's bones are going to leave some fossils for the next generation to discover. That's how you can come to a rudimentary idea of how old a fossil is. We got better methods nowadays for dating fossils as well. We can use what's called radiometric dating, where we check the ratio of certain radioactive isotopes existing in these rock layers, and we can use that to determine exactly how old a fossil is, exactly how long ago it was that that particular organism died and stopped exchanging materials with the environment. So we have all kinds of ways of figuring out how old fossils are. And we find different organisms sitting in different layers of these rocks. So if you go really, really, really deep in the fossil record, you can find an organism called Pakicetus, which you can see right here on this chart. There's some Pakicetus bones that we've uncovered. We think Pakicetus probably looked a little bit like this. It's a mammal, it's a water foraging mammal. It goes into the water periodically, but it can come out on land periodically as well. If you go shallower in the fossil record, more recent, then Pakicetus starts to disappear, but you do start to see fossils of another organism called Rhodocetus, which looks a little bit like this. And you can see that these organisms kind of appear to be related. But in the strata of rock where you find Pakicetus, you do not find fossils for Rhodocetus. So Rhodocetus appears to have just showed up later on, shortly after Pakicetus kind of started to wane away and disappear. And you can see that Rhodocetus, he's spending more time in the water. He's got these webbed feet, he's got an elongated snout, he's more adapted for swimming in the water. Now, eventually, you stop seeing Rhodocetus show up, and instead you see something called Dorudon. Dorudon is another mammal, but this one is very, very well adapted for living in the water. You can see that the back legs doesn't need them anymore, so they have shrunk down to almost nothing. But if you look, there's still the bones for those back legs existing in Dorudon. You can still see the little remnants of those bones, but it's still using its tail, almost like a flagellum, actually, in order to propel itself forward, and now its forelimbs are kind of changed into these flipper structures. But the bones in its forelimbs have not actually changed. They're a little bit shorter or longer or thicker or thinner, but the arrangement of the bones is exactly the same. We don't have Dorudon today. Dorudon's not around. We know about it because of the fossil record, but we do have beluga whales, which have a lot of traits in common with all of these different organisms. So it's very possible that one of the ancestors of beluga whales was one of these fossils that has been left behind right here, or an organism very closely related to the individual that left that fossil. So this is a lot of what paleontologists do. They look at fossils, they draw analogies, they draw comparisons to what modern organisms currently look like, and then they try to arrange them in a timeline based on how old the fossil was, and when certain organisms show up, and when other organisms disappear, in order to create this kind of story. Now, one thing that you've probably heard about related to the fossil record is the concept of the missing link, right? The missing link. Ah, look at this. You've got all of these fossils, you got one form, and then another form, and then another form, and then another form, but where's the missing link, mister? You need to show the transitional form between all of these. There's a problem with the concept of the missing link, though. Let's say we have an organism that's left lots of fossils for us to find, and we've put together a timeline of different transitional forms here. Let's see, we have... And we have 3 fossils, right? We have fossil A, we have fossil B, and then we have a modern organism. So we have this nice chain of events. We say, okay, an organism showed up at this point and they looked like this. Then later, that organism disappears and we have fossil B showing up, and that looks a little bit different from fossil A, but a little bit closer to this modern organism, and it shows up about halfway in between, so that's probably a transitional form right there. And then we have this modern organism that looks like this. And then someone will say, but where is the missing link, right? You should have a transitional form here and here, in order to show the progression from fossil A to fossil B and then fossil B up to the modern organism. So then these hardworking paleontologists will go out and they will find that missing link. They will find an organism that fits right in this area. We'll get one right here, and we'll get a fossil right here, and they'll say, aha, okay, now we have a much more complete fossil record than we did before, and yes, it supports our hypothesis that the organism that left fossil A was an ancestor to the organism who left fossil B, which was an ancestor to the organism that is still alive today. But then, someone might come along and say, whoa, 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 not so fast. Before, you had 2 missing links. Now you have 4 missing links. You have half as much evidence as you had before. Checkmate. The fossil record is actually staggeringly complete, considering that only organisms that die in sedimentary rock actually leave their fossils behind, and not all of them are going to leave intact fossils that are amenable to being analyzed in this way. You know, we do have mountains and mountains and mountains of fossils, but we're never going to find every single transitional form between organism A, organism B, and the modern, because every single individual in that family tree is a missing link. You're a missing link, okay? So, the fossil record is incredibly complete given the limitations that it has. But we don't have to rely simply on fossilized evidence in order to know about how organisms have kind of changed over time. We can also look at something called biogeography. So geologists have done a very, very good job of figuring out how old the Earth is and how land masses have shifted and changed thanks to plate tectonics and climate shifts and all kinds of things, how Earth used to look in the past at various points in time. And then we can take all the information that we've gotten from the fossil record, we can lay those two timelines over top of each other and see what kind of new insights we get. And this is called biogeography. Biogeography is the study of the geographic distribution of species. Where do things live, how did they get there, and why do they live there? One of my favorite demonstrations of the concept of biogeography is the koala bear. Koala bears are marsupials, and you've probably heard of other marsupials as well. Kangaroos are marsupials. Wallabies are marsupials. There's another kind of organism called a tree kangaroo, happens to live in Australia, and it's exactly what it sounds like. It's a kangaroo that climbs trees. In fact, if you really consider it, just about every marsupial lives in Australia. They're all kind of concentrated there in Australia. The only marsupial that lives in the United States is the possum. That's the one extant species of marsupial that we have here in North America. But all the other marsupials, they live in Australia. So why might that be? And another interesting thing is that there's not a lot of placental mammals in Australia. There's bats, but bats have a pretty easy way to get to Australia. Bats can fly, so they can kind of go wherever they want. But pretty much every mammal in Australia, every native mammal that hasn't been introduced, is a marsupial. So how did that happen if they aren't showing up anywhere else? Well, the fossil record tells us that marsupials are an older form of mammal. Marsupials showed up first, and they did quite well for themselves. So they spread all over the place. Now, this was when all of the continents were together at that time. So when we had Pangea, or one of these other supercontinents. So the marsupials were able to spread. But then Australia broke off from the rest of the continents with all the marsupials that happened to be living on Australia at the time. Meanwhile, in the rest of the world, a new kind of trait showed up. The trait of having a placenta. Placental mammals like us started showing up. And as it turns out, there's a lot of advantages to that. So placental mammals kind of took over everywhere else. All the other marsupials started to go extinct on the mainland, but the placental mammals, they did very, very well for themselves. They rose up, and the only marsupial left turned out to be the possum. But the marsupials on Australia weren't participating in that competition. Mutations arise randomly. They show up randomly. So if you had a bunch of mutations occurring on the mainland, which ultimately caused placental mammals to rise up, you would not get those same mutations showing up on Australia, or it would be very, very unlikely that you would get the same mutations showing up on Australia. So Australia continued its own evolutionary development with marsupials, and you got all kinds of different marsupials. You got the kangaroo, you got the wallaby, you got the koala bear. There's a kind of marsupial called the Thylacine, or at least I should say there used to be a kind of marsupial called the Thylacine, which is a predatory wolf-like marsupial. It's the Tasmanian wolf. It went extinct relatively recently. We actually have video footage of them. Black and white, but we have video footage of them. And the number of marsupials on Australia is consistent with our understanding of everything about the theory of evolution by natural selection and the way that land masses have shifted around over time. You can take this idea a step further. You can see that land masses that used to be connected at a certain point in geological history, they will have the same fossils. They'll have the exact same fossils on the parts of them that were connected. So say the east coast of South America and the west coast of Africa, if you were to look at a map, you could see that those parts fit nice and neatly together. And because they used to be connected, all of the organisms that are native to those areas developed from the same ancestral organism. So let's say you take two plants, one from the east coast of South America and one from the west coast of Africa. If you sequence their genomes, you might find that they are more closely related than you would expect for two plants that are so distant from each other. So this is the idea of biogeography. And this has added yet another layer of support to this idea that organisms have shifted and changed over time.